f minus 1 of A union f minus 1 of B, or union of pullbacks is equal to the pullback of union. This relation is the same as previous relation, as previous equality, and I will go further. Next relation is f minus 1 of A C. Let's define AC is a complement of the set A. Assume we have some X here, and here some Y, and here we have some subset A. In this case, the complement of A, this is denoted as AC, or complement of A. And of course, let's draw here a pullback f minus 1 of A, and in this case, this is f minus 1 of AC. So f minus 1 of AC is equal to f minus 1 of A, and then we take a complement. So this set is mapped into this set, and this complement is mapped into this complement. Next, let's define what does it mean to be countable. The set subset sometimes is called countable, and sometimes this set is uncountable. What does it mean? Set X is countable by definition. We can construct a mapping from this set X into the set of natural numbers. In other words, we have one-to-one correspondence between elements of the set X and the set of natural numbers. Or in other words, we can count element of X. For example, if we have some set X, and we have elements here. Here we have the set of natural numbers. And set of natural numbers consist of 1, 2, 3, 4, and so on. And that's why we can construct a bijective. I have to say that this F must be bijective. This is one-to-one correspondence. So we can map the first element into 1, the second element into 2, third element into 3, the fourth element into 4, and so on. In other words, we can count elements 1, 2, 3, 4, 5, and so on, elements of X. In this case, X is called countable set. If we cannot do this, in this case, our set is called uncountable. So we have 3 kinds of these sets. Set can be finite, with finite number of elements. It can be countable, and we can count elements of this set, or in other words, we can construct bijective mapping from X into set of natural numbers. If our set is infinite and we cannot construct this bijective mapping, our set is called uncountable. It means that this set has too many elements, and we cannot count the element of this set. The most important example of countable set is the set of rational numbers. Set of rational numbers, as we know from the course of arithmetic, watch our arithmetic playlist, is the set of numbers that can be represented as P over Q, where number P is integer and Q is natural. So this is actually the set of fractions, and the numerator of this fraction is integer number, and it can be positive or negative. We can easily construct bijective mapping from this set of rational numbers into the set of natural numbers, or in other words, we can count element of this set. How it's done? We can write elements of rational numbers as 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. So in first line, we write all elements where numerator has 1. Of course, we can also include negative numbers, so we have plus minus 1. And next, we have to write 2 over 1, 2 over 2, 2/3 and 2/4 and so on. Plus minus, plus minus, plus minus. Here we have 2 elements in each element. It doesn't matter. Next we write plus minus 3/1, plus minus 3/2, plus minus 3/3, plus minus 3/4, and so on. Plus minus 4/4, and so on. We can continue this up until infinity, but we can write rational numbers in this way, and any rational number will be in this table. Next, we can easily perform mapping, or we can count elements of this set. How it's done? Easily. It's done in the next way. And so on. So we can calculate elements of this set, counting its elements like this, and we can count it. For example, it will be the first element, this is second element, this is third element, fourth element, fifth element, and so on. So Q, rational numbers, are countable. Next, we will show that R, which is set of real numbers, uncountable. Let's prove that set of real numbers is uncountable. It's enough to show that this segment from 0 to 1 is uncountable. And we prove that this segment is uncountable using so-called Cantor diagonal argument or diagonal method. First of all, we have to make assumption that assume we have number 0.2, and in decimal representation, this number also can be written as 0.1999 and so on. So second number consists of infinite number of nines, and these two numbers are equal. Let's assume that we do not have this kind of decimal representations, and for any number with finite number of non-zero digits in its representation, we have only this kind of representation. And next, let's begin our argument. So in segment of 0, 1, we have uncountable number of elements. So we cannot count an elements of this segment. Assume that number of elements or number of numbers in this segment is countable. We assume that number of numbers in this segment is countable. And next, we have to have a contradiction. We assume that we have countable number of numbers in this segment, and let's have a contradiction, which means that assumption that we had countable number of elements was false. And this means that number of elements was uncountable. Okay, so let's begin our proof. Assume we have countable number of elements in this segment. First element, R1, is equal to 0. Some digit, A11, N12, N13, and so on. Second element is also inside this segment, 0, 1, and also can be represented in its decimal form as A21, A22, A23, and so on. Along the same way, next number has a representation A31, A32, A33, and so on. So assume we have countable number of elements in this segment, and these numbers, of course, A1 is some digit. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And let's find another number, call it number S. Let us write S is equal to 0, next decimal point, and some number, B1. How B1 is defined? B1 is equal to, assume this number, A11. Let's fix some number 2. for simplicity. Number 2, if A11 is equal to 2, we have to take B1 not equal to 2. Let's take B1 equal to 1. So if this number is 2, let's take B1 equal to 1. Next, if this number A11 is not equal to 2, in this case, B1 will be 2, okay? So in any case, B1 is not equal to A11. Next, B2, next digit of decimal representation of our number S, B2, is defined using same argument. If A22 is equal to 2, B2 is 1. If A22 is not equal to 2, in this case, B2 is equal to 2. So this number B2 will be always not equal to A22. And we will define B3 along the same way from this digit A33 and so on. Of course, S, this number S will not be, S is not equal to R1 because B1 is not equal to A11. So S is not equal to R2 and S is not equal to R3 and so on. So we found an element, number S, which is not in this list, but we assumed that our set is countable and we found another element not in this list. And this is a contradiction, which means that number of elements in this segment is not countable. That's all. So the proof is over.